The next topic of discussion is Rapid Spanning Tree Protocol, or Rapid STP. The IEEE designation for Rapid Spanning Tree Protocol is 802.1W. Now, spanning tree takes a total of 50 seconds to converge from going from blocking to forwarding. If you remember, from blocking to listening, it takes 20 seconds. Then between listening and learning, it takes 15 seconds, the time being called forward delay. And then between learning and forwarding, it takes another 15 seconds, and that time also being called forward delay. 50 seconds is too long of a time for users to wait before they can transmit data. Rapid Spanning Tree, however, goes through a quick proposal agreement process before users can forward data. Now, the Rapid Spanning Tree port's roles and states have changed slightly. Ports upon power-up are put in the discarding state when Spanning Tree has its ports in the blocking state. When Spanning Tree transitions to the learning state, Rapid Spanning Tree is still in the discarding state. Now, these states are named after what the switch is doing to user data. So, of course, in the discarding state, Rapid Spanning Tree will simply discard user frames. Then you go into the learning state, where you're learning your MAC addresses and populating your MAC address table exactly like Spanning Tree, and then you go into the forwarding state. However, this succession of state changes happens quicker in Rapid Spanning Tree than it does in Spanning Tree. Spanning Tree, so to say, is timer-based. Rapid Spanning Tree goes through a quick proposal agreement process between two switches before the ports can go into forwarding. So since Rapid Spanning Tree is based on a quick proposal agreement and is not timer-based, let's go over that quick proposal agreement statement or proposal agreement process. Now, on this diagram here, I have switch 1 connected to switch 2 over port F0/1 on switch 1 and F0/1 on switch 2. Now, we're going to assume that switch 1's MAC address is AAAA. Now, folks, I know that AAAA is actually 16 bits, not 48 bits, and a MAC address is supposed to be 48 bits, but I just don't have the space here to write 48 bits worth of A's. So, each hex character is 4 bits, which makes AAAA 16 bits, but we're going to pretend that this is just 48 bits. Switch 2's MAC address is BBBB. Now, the bridge ID field in Rapid Spanning Tree, or per VLAN Rapid Spanning Tree, remains the same. 4 bits for priority and 12 bits for VLAN ID, which would make the default priority for this switch 32768, just like with Spanning Tree. And let's presume we're just running VLAN 1, which would make the priority field a total of 32769, 32768 plus 1. Same with switch 2, the priority would be 32769. So the tiebreaker in this case would have to be the MAC address. And since switch 1 has a lower MAC address than switch 2, AAAA in hex being lower than BBBB in hex, switch 1 we know is the superior bridge. Now, each one of these switches sends itself, upon power up, a proposal BPDU. So switch 2 sends a proposal BPDU to switch 1, and switch 1 sends a proposal BPDU to switch 2. This proposal BPDU is actually, in the proposal BPDU, the switch is actually claiming that it will have the designated port on this segment between switch 1 and switch 2. And if we remember, a segment is a connection or a link between two switches, right here, between switch 1 and switch 2. So in each switch in its proposal is claiming that it will have the designated port on the segment. And if you remember how things worked out in Spanning Tree, the superior switch always ends up having the designated port on the segment. So switch 2 sends switch 1 a proposal saying, I am going to have the designated port, or as in, my F0/1 is going to be the designated port on this segment. Switch 1 rejects switch 2's proposal BPDU because switch 1 is clearly superior. Switch 1 also sends a proposal BPDU to switch 2. And switch 2 sees that yes, switch 1 in fact is superior, and switch 2 accepts switch 1's proposal BPDU. At this point, if switch 2 has any downstream ports, it puts all these ports in the discarding state. And this process is called synchronization. So switch 2 synchronizes itself, basically isolating itself from the rest of the topology if there are other switches down here. And this is done in order to prevent temporary layer 2 bridging loops. So you isolate each segment away from each other segment to lessen the chance of having a layer 2 loop. At this point, switch 2 sends back an agreement BPDU and makes its F0/1 into a root port. So this agreement BPDU reaches switch 1, and switch 1 makes its F0/1 into a designated port. Now both these ports are put in forwarding, and the proposal agreement process between these two switches is over. And it then moves one segment downstream, where if switch 2 is connected to, let's say, switch 3, the same process will happen between switch 2 and switch 3. Now, as you see, this took a total of maybe 4 seconds, as opposed to 50 seconds with regular spanning tree protocol. So if you remember, BPDUs are sent in spanning tree, whether it be regular spanning tree or rapid spanning tree, every 2 seconds. So the first 2 seconds were for the proposal BPDU, the next 2 seconds were for the agreement, and within 4 to 6 seconds, these switches have put their ports in forwarding as opposed to waiting 50 seconds. This concludes the rapid spanning tree lecture.